Yeah, there we go. Great. Thank you, Jamie. So welcome and thanks for joining us for the Municipal Alliance for Adaptive Management April meeting. We're really excited. We're going to roll out a presentation on some stormwater storm impact research presentation today. So that should be a really interesting meeting for us. There's a lot going on right now. We'll start with introductions. I'm going to start in person and then we'll go to remote. Gretchen Young, City of Rochester, and I am a voting member of MAM.
Kala Matzo from PrEP. Tim Bolts, City of Dover.
Mike Tibbetts, Berwick Sewer District.
Sean Gregg, Town of Newmarket.
Lindsay Butler, Town of Newmarket.
Bill McDowell, University of New Hampshire.
Michelle Shattuck, University of New Hampshire.
Dennis Massey of South Berwick Sewer District.
Great. All right, we're going to go to the screen then, and there's some names that are newer to me. So if I don't say it right, I apologize. But we'll start. Chris Whitney.
Hi everyone, Chris Whitney. I'm a program scientist at PrEP.
All right, Stacy Villanueva.
Hi, I am with Brown and Caldwell, MAM Technical Advisor.
Great, thank you, Stacy. All right, Clifton Bell.
Clifton Bell with Brown and Caldwell, also in MAM Technical Advisor.
All right, Atsuchi.
Hi everyone, Atsushi Matsuoka from University of New Hampshire, working with Carter. Nice to meet you.
Nice to meet you. Thanks for joining us. All right, Jake Roger.
Jake Roger, Town Administrator in Epping.
Slava.
Hi, Slava Lubčić, Maryland Center for Environmental Science.
Great, thanks for joining us. Mike Babinski.
Oh yeah, Mike Babinski, Public Works Director, City of Somersworth.
Great. John Storer.
Yes, good afternoon, John Storer, Director of Community Services for the City of Dover.
Excellent. Sally Sewell.
Thanks, Gretchen. Sally Soul. I'm with the Non-Point Source Program at the New Hampshire Department of Environmental Services.
Great. Ken Edwardson.
With New Hampshire DS, Senior Scientist, Water Quality Standards.
Excellent. Daniel Gaeta.
I'm Danielle. I'm with the Permits Branch at EPA Region 1.
Nice to see you, Danielle. You're quiet, but I think that's okay. Jim Steincross.
Hi, Jim Steincross with Roth Young Pignatelli on behalf of the City of Rochester.
All right, Daniel McAdam. You're still on mute there, bud.
UNH Stormwater Center, and I lost my voice. So I'll just
oh no. All right. Well, then we won't make you talk much. All right. Jumping around, Jamie McCarty.
Good afternoon. I'm Jamie McCarty with the City of Portsmouth. I'm the Operations Manager for GIS and Stormwater.
All right. Judd Kenworthy.
Hi. I'm Judd Kenworthy. I'm one of PrEP's external advisors working with Cal and his team.
Great. Thank you for joining us today. And is it Chiaki?
Hi, I'm Chiaki Motegi. I'm a research scientist at PrEP. Thank you.
Great. Thank you. I'm not sure. Steve Kucher, you're welcome to.
I think he said he was just.
Yep, that's fine. That's fine. And Jay Wheeler?
Present.
Great. Anyone else that I missed? I don't think so. Okay, we'll get started. Usually have Suzanne here to make sure we have a quorum, but I think that we do. So just approval of the February 5th meeting minutes. Did anyone have any questions about those minutes? All right, can I get a motion to approve them?
Motion to approve the minute.
All right, Dennis Messier, do I have a second? All right, Tim, thank you. Tim from Dover. So then I'm going to take roll call. Start Gretchen Young, yes. Tim?
Yes.
Dennis?
Yeah.
Yes. Is it?
Great.
Greg? Oh, no, Greg's not.
Mike was.
Mike, are you?
I wasn't part of that meeting.
Okay, all right. Then we will go to Jake.
Jake Roger, yes.
Yes, all right. Who else do we have? I think that
Jay Wheeler was there.
Jay Wheeler, yes. Jay. Can't see him anymore. Oh yeah, there we are. Jay, are you a yes? Yes. All right, great. Well then that, thank you. We'll close, or Jamie McCarty, actually, if you want to vote for Suzanne's not here yet.
I vote yes.
All right, great. Thank you. We will move on to the meat of this meeting, and it's the UNH storm impact research. And I will turn it over to Michelle and Bill to take it away. Hi, Suzanne. Suzanne Woodland, just arriving.
Well, first I'd like to start as I go through the share screen with a real thank you to the ma'am for having the maybe audacity, but having the ability to support this research, which I had felt for a number of years would be an important thing to do as we shape the management of the bay. And I'm really glad that we're able to do it now.
Great. So
our presentation today will include this, sorry, the presentation today will include the two parts. First, our work on some specific storms, and
on your, oh, it's probably Gretchen's screen.
I'm hoping Jamie McCarty is going to be on that.
Somebody okay that, but I can't get up to that. Okay.
No, it's good.
Two parts will be first on a project where we assess the impact of storms on river water quality, especially with a focus on the particulate matter. And then we look at the impacts of, the ability to estimate flow in the rivers which are currently ungauged. Both of these, of course, both the river volume of water and the impact of storms on water quality in the bay, both of these are important issues for understanding how the bay functions as an ecosystem. And so I will do the first part on the impact of storms, and Michelle Shattuck, who's here on my left, the second part. Okay. Yeah, I can't, I seem to be on a different screen in terms of.
I think so.
Work great test, but now it doesn't, can't. It's weird. It was working great.
Jamie McCarty, I don't know if there's any
settings.
Yeah.
Yeah, I would suggest try just sharing the application again.
Yep. No dice.
Wow.
This is really.
You should have left that up.
I'm sorry.
Oh, bummer.
I've never seen this happen.
Yeah, I don't know. It's almost like we've got.
Do you have
We're on two different screens.
do you have a thumb drive with it by any chance?
It's on.
Here, wait, let me see. Are you definitely sharing the screen?
I think what's happened is that I'm on the wrong screen, but that's weird. It's a mouse move, but the controls Now we do. All right. Sorry for that delay. So the context of this work has to do with the well-known and unfortunate and continuing, ongoing decline in eelgrass coverage in Great Bay Park. And we see here from the recent paper, McCoulis et al., as a PhD student at UNH, that this is plotting up the steady decline and an increase in light attenuation. And we care, of course, because eelgrass is the keystone species within Great Bay. We've lost a lot. It's sensitive to light availability, and one of the drivers of light availability is particulate matter, as well as the, as you see in that list, the nitrogen content of the water can affect the turbidity and indirectly by affecting chlorophyll A, and the organic matter in the water, as well as the suspended particles, suspended sediment in the water. And so we have these three figures that I've already highlighted, the first two, the declining eelgrass, an increase in light attenuation, which means it's getting more turbid over time, and at the bottom panel is the low tide total suspended solids, or TSS. Each of these is suggesting that the eelgrass, as well as the light environment, is getting worse over time. Now, we ask the question next, then, what is driving these changes? And what we see is that the rivers are very important in controlling what's happening in the bay. And so we see in the first couple panels, the dissolved inorganic nitrogen, or DIN, and at high flow, the concentration is actually going up. And at high flow, the phosphate concentration is actually going down. These are data high flow in the rivers and the response in the estuary. And we see the dissolved organic carbon, the middle panel, and total nitrogen are also increasing when the rivers are running high. Now, interestingly, because we know that particles can be affected by river flow, sure, we actually don't see strong relationships between the particulate nitrogen, this far right panel, or the total suspended solids. Of course, the particulate nitrogen is a part of the total suspended solids, but neither of these measurements shows any responsiveness to total river discharge. Now, this is a bit surprising, and it led us to question whether we were sampling at the appropriate time to document the particles that are actually entering from the rivers. Because, of course, storms stir up sediment particles, and they don't stay in the water column for all that long necessarily. So there's a zillion papers in the literature. This stream, this storm, the big storm comes, the total suspended sediment could go up, and it could go up literally 1,000 times higher in many places, from base flow to storm flow. So if you want to understand particles in rivers, you really got to get some idea what's going on in storms. So our analysis that we've done so far, this McCoulis et al. 2026, is based on monthly grab samples for many years at the head of tide. And they were not timed to try to capture the high flows, because, of course, it can be even dangerous to do that. Mm-hmm. And it can be inconvenient, and it may, for the other parameters, it may give us a bias the other way. So we asked the question then. Here's the one that you already spoke of. Given that the TSS is not responding on a monthly sample basis, is it responding during storms? And so I am going to just skip this and go right. We can talk about that if there's time later. I don't want to spend too much time on all the figures from this paper because it could be a deep dive for the points that we need to make. So the freshwater storm impacts, how are we going to characterize those? Well, what we proposed and what we did was to use the sensors that we have available in our UNH water quality lab to provide some insight into the impacts of storms on the bay. And the question we asked, shown in the bottoms here, is do storm inputs nitrogen, total suspended solids or sediment, TSS, and colored dissolved organic matter, the yellow CDOM that we heard referred to. Do storm inputs drive their variability in the concentrations of these parameters in the Great Bay system, in the estuary itself? And so to do that, we deployed XO2 sondes. So these are YSI XO2, that's just the name of the sonde, it's widely used. We used them a lot in previous research. They're really the standard at this point. They're rugged, they're reliable, we really like them a lot. So we put them in the Lamprey, the Exeter, and the Winnicott rivers. And we compared that in during the storms, following what's going on in the river, and then we follow what's going on in the bay using the sensors that are already in place on the Great Bay buoy, which is out in the middle of the bay. And so with this XO2, we can measure turbidity and fluorescent dissolved organic matter. Notice it's FDOM, and I'm going to use these terms even though, just think, anytime I say DOM, it's like the colored stuff in water. It's CDOM, depending if you measure it one way. It's FDOM if you measure it a different way. They give you the same answer. It's the same stuff. It's the yellow colored stuff in water. So we have FDOM sensors, we have turbidity sensors, and then we also took grab samples to measure directly the particulate carbon and the particulate nitrogen that's in the storm water that's being delivered from the rivers into the bay. Now, it's important to keep in mind the context and looking at the actual units, because we're going to spend some time looking at actual units. So 30 of this FNU, the fluorometric nephelometer units, they're not formazine nephelometric units. You don't need to know that, just FNU. It's a measure of turbidity. It's about 30, it's as high as it's ever gotten in our, over 15 years of record, almost 15 years on our sensors in Lamprey River at the Wiswall Dam. So it's not at the head of tide, but it's a little bit further up. But this record suggests that, well, at least up there by Wiswall, it's not responding too much to storms. Some of these are really big. Storms. It's a very complete record. And so, for context, then, with this high of 30 FNU in the Chesapeake Bay, the Susquehanna River maxes out at over 800 NTU, which can be it's easily converted to FNU. It's basically the same unit. So 30 in the Lamprey at highest flow over almost 15 years, 800 in the Chesapeake. So it's like, wow, that's not too big a change that we see in response to storms in the Lamprey. But is that really representative of what's actually going over the head of tide and the rivers that are not the Lamprey River? So that's what we set out to look at here. So we have a study period in 2024 and 2025. We used the biggest storms that were collected during those periods, and should note in all of these that the 2025 storm is just much, much higher than 2024. So you set out to study storms, you get a dry year. That's like guaranteed. So this year, we should definitely have a storm study and drought will ensue, and then maybe grass will come back. Anyway, so what we see is that in the end of this period of record in late October of 2024, over here, and in around May of 2025, we have the biggest storms during our months of recording when we had the sensors out and we had the auto sampler in place and we're ready to do the lab analysis. So we're going to look at these two storms in some detail. And again, note that this is two. I don't need to read it there. I can read it here. It goes up 2,000 CFS in 2025, the Lamprey, and it's only 300 in 2024. So it's a 10 times bigger storm in 2025. And you can see right off the bat that the Great Bay buoy is like pretty constant and pretty low during this period when there aren't a lot of storms, with the river not behaving. It's not putting in a lot of flow. And then during the storm, it goes up. But you also want to note that the turbidity in the Great Bay buoy, even when it's not at storms, is much higher than the turbidity in the Lamprey. So again, look at the scales. The Lamprey, the scale is only up to 6 or 8 on the right-hand panel. And in the Great Bay, the scale is up to several hundred, over 100 in both of those panels. And so right off the bat, you say, well, it looks like this is, the Great Bay is much higher sediment than what's being delivered to it by the Lamprey, the largest tributary. And so we also asked the question, is the fluorescent FTOM, the fluorescent colored organic matter, how would that respond to the storms? And what we see is that in the 2024 storm, it didn't respond much at all. And in 2025 storm, there was a very noticeable peak in the fluorescent organic matter in the Great Bay buoy, as evidenced by the buoy right here, and also only a very small increase in the Great Bay buoy. But basically, the FTOM is responding or is similar in the buoy as it is in the bay, as evidenced by the buoy record, compared to the river. So they're fairly comparable, and the units are similar. Here, the peak is 80, and in the bay, and 80 in the river, and it's 90 in the bay. So the buoy is capturing the river input. The river input has a clear imprint on the buoy in the bay for the fluorescent FTOM, and it does not for particles. So we also looked in detail at individual every 15 minutes, maybe it was even more frequently, very, very fine timescales to track what happened actually during the storm in the Exeter and the Lamprey rivers, because we know as biogeochemists that we'd expect some increase in the turbidity, and it's not changing very much. It's really pretty stable. This 2024 storm shows almost no change. And in the big May storm, we see what we call hysteresis, and that on the way up in flow, the turbidity is lower, a little lower, and then the way back down, it gets a little bit higher. And but again, if we look at the scales, it's only going up to 8 units of 8, or maybe 9 or 20, depending on the river. So I think this is one of the key slides to take away. So we've got this the rivers have responded to storms, they do this and that, and turbidity is changing, we're seeing there's a change, but how does it compare to the changes that are occurring in the bay? So what we've done here is plotted this storm, the November 2024 storm. The green here is what the Exeter was doing during the storm, and its flow at that time. And the blue is the lamprey during the storm. And the brown, the one that goes up and down, that's what's happening in the bay. So, and we're plotting that discharges, the combined sum of Exeter, Lamprey, and Winnicott River discharge. So more water going into the bay, much higher concentration of turbidity and thus TSS, much higher turbidity and thus concentration of TSS, and yet it's not being brought in by the river. The likely only logical explanation then is the rivers are doing something. They're bringing in a lot of water. It's churning up everything in the bay. Could be also affected by winds and tides and everything else. But the rivers are not bringing in the sediment that we then go see and care about and worry about in the bay. It's being generated in town. So this image of 10 times higher concentration in the bay during storm compared to what's in the rivers is, I think, centrally important. And so same for the May storm, very, very similar. The rivers don't do much. They do a little bit. You can see like the green here, the Exeter, yeah, it's going up with flow, but it's nothing compared to the way the bay goes up and flow. So again, two different storms with very detailed assessment in these rivers now. It's generated inside the bay. So we had a similar high frequency sampling on the dissolved organic matter, the FDOM. Not going to walk through these. It's the same thing. It's sort of squirrely back and forth. It's not easily predicted by flow, with the point of showing these. In some other rivers, these curves look much cleaner, and they are predictable by flow, but not in our rivers. And here for the fluorescent organic matter, the same thing. It's like, well, this one in the middle, it's like going up at high flow in the lamprey, and but it's not a huge increase. And many places we might expect to see actually a decline. In some, we might see a decline in some places and a full increase in others. But so the behavior of the rivers is kind of muted. It's not atypical for shallow gradient coastal rivers, and the bay is generating its own turbidity, but it is influenced by the FDOM, which is the next point. And we see here the same plots where we show the two rivers and the response in the bay. And what we see here is like the rivers actually have higher fluorescent organic matter compared to the bay. And during the storms, it didn't really change much. That's the small November 2024. And in May of 25 storm, it's like, yeah, the rivers are higher, wetland sources of FDOM. And the bay is pretty unresponsive to the flow, and the rivers are not very responsive either. And the rivers are a little higher, and it gets diluted out in the bay. And that all makes sense based on what we know about the So if we turn from turbidity to looking at TSS, so we can talk about loads. Turbidity is a decent proxy. It's not a super great proxy, but it's the best we've got for TSS. So we want to predict total suspended sediment from the turbidity sensor. We can use this relationship. We saw a similar relationship in total between flow and, turbidity and TSS across a range of flow in a bunch of other small tributaries in New Hampshire. And it's pretty similar relationship. This is not unusual. Typically, this is this can be done with about this level of certainty, which is fairly good, and it gives us a good handle on what's going on. Fluorescent organic matter is also related to the dissolved organic carbon that we measure directly. It's also related to the dissolved organic nitrogen that we measure, and the relationships are, there's a relationship there. Statistically, it's a decent predictor. It's not a one-for-one, but it's useful. And so I want to finish with this look at the carbon and nitrogen ratio in the sediments of the bay, and then the particulates that are being brought in from the river. And so what we see is that the carbon and nitrogen ratio, why would I get on about that? What is it? The carbon and nitrogen are two of the most important and the largest contributors to the total mass of organic matter that's coming off the landscape. So like leaves, dead eelgrass, soil particles, the carbon is dominant and the nitrogen is a smaller fraction, but that carbon and nitrogen ratio is indicative of the nutrient status in the place where those particles were formed. If it's a farm field versus a forest, here in New Hampshire, we might say the farm field can have 10, a C10 of 10, but a forest, C10 around here, this forest 25. So what we see then, if we look at the particulates in the bay and the sediment in the bay, we see that the ratio is about 10 to 12. And I'm still puzzling over this, but the ratio in the rivers is quite low, and suggesting that it is either of microbial origin or a very nitrogen-rich plant material that's coming in. And so, as a biogeochemist, I'm like, wow, that's like, well, how come? Why is that? But for managers, the point is simple. It's simpler than worrying about why one's higher than lower. They're not the same. So the stuff that the river is bringing in doesn't look like the stuff that's in the bay and generated and sampled in the bay. So the material that's in the bay has double the carbon to nitrogen ratio of the stuff that the river is bringing in. So this is another important bit of information that suggests, like, no, the rivers are not driving it's not driving the particle load, maybe driving particle generation, that whole separate question about hydrodynamics and something else. But it's not the material from the landscape that's ending up in any given storm in the bay. Maybe it came from there 1,000 years ago, or 10 years ago, 50, but it's not the same stuff that the river is bringing in right now. It doesn't look the same. It doesn't behave the same in terms of concentration in response to storm. So from that, we have the following conclusions. First, turbidity does increase in these freshwater rivers during storms, but the increase is small. And it's not anything to be excited about as an environmental scientist. It's just kind of like, wow, it's amazing how small it is, really. The turbidity within Great Bay during storms is 10 times higher than the river inputs. That's a big difference. These sensors are quite sensitive, and it's easy to say 10 times difference is a big difference. And the nature of the particulate matter in the bay, the stuff that's floating around that you can see in the bay, is similar to what's in the bottom of the bay in its bay sediment, but it's not similar to the river particulate matter. So, Great Bay turbidity, in my assessment, is driven by internal sources. Now, today, I can't tell you whether it was 50, 100, or 1,000 years ago, but right today, it seems pretty clear. And in contrast, the rivers drive the Great Bay dissolved organic matter, the CDOM, especially during large storms. And we kind of knew that about the CDOM from previous publications, a previous publication from UNH. But this is the first time we've really gotten a handle on the particles. And so How do I do for time?
No rush.
Okay.
Yeah. take your
So
time.
questions, comments,
Do we want to get through this?
shall we go through the? All right,
What
we'll
do
go
we-
through. We'll go through the next topic.
Yeah, go for it.
Okay.
Yeah, I guess, yeah, folks
then-
can hold their questions and we'll.
Okay,
Yeah,
we'll
yeah.
do that. That was our original
What do we
plan.
have for tweets? So Zoom kick us out at a certain time? Nope.
Nope. Okay, and now Michelle will talk about some of the work that she led on river flow.
All right, thank you all for being here. For those of you who don't know me, I'm Michelle Shattuck, like I said before, I'm a research scientist at UNH, and Bill and I have worked together for many years on biogeochemistry stuff. Rivers draining to Green Bay, the river. I've also helped out do the nitrogen loading analysis or the calculations for the last 2 rounds of the state estuaries report. So, but now we're going to kind of take a look at a smaller component of this project, which was focused on how discharge is estimated in the different Great Bay tributaries. And to do that, I'm going to take a kind of a deep dive using a runoff comparison, which I'll explain as we move through these slides. So before, Bill was focusing on the 3 of the tributaries that drain to Great Bay proper. Now I want to take a step back and look at all 8 tributaries that drain to Great Bay. 5 of them have USGS gauging stations, and I should step back and first say the our monitoring sites are located here at these black circles. The black outlines represent each watershed boundary, and 5 of these tributaries have active USGS gauging stations in them. Those are shown with the black triangles. The Winnipeg is the only station that is actually co-located with the USGS site. So the other 4 tributaries, the Exeter, the Lamprey, Oyster, and the Cachico, have USGS gauging stations upstream from our monitoring sites at the head of time. Now, the Bellamy, the Salmon Falls, and the Great Works River currently have no USGS gauges active there, but we did dig up some data from 2 inactive USGS sites on the Salmon Falls River. So those are really useful in this analysis that we're doing today. And then you can see other older inactive USGS stations in gray triangles throughout this map. Okay, so the main task for this part of the work was to review the methods used to estimate discharge at monitoring sites on both the 5 gauged tributaries and on the 3 ungauged tributaries to start to assess whether these methods were appropriate. And then if necessary to determine where we might appropriately measure discharge in rivers that don't have gauges, the Salmon Falls, the Great Works, and the Bellamy rivers. So first I want to walk through this table that kind of shows how we're currently calculating discharge in these tributaries. First column is the tributary monitoring station, followed by the upstream watershed area, the USGS site that we're using to calculate discharge, the area upstream of the USGS gauge, and then finally on the right, we have the ratio of the downstream tributary monitoring station to the USGS gauge, and we use that as a flow multiplier to estimate discharge at those sites. So here we see again, the Winnipeg is co-located. We don't need to adjust that discharge. The Exeter, Lamprey, Oyster, and Cachico are all estimated from upstream gauges. And then the Bellamy River, in previous State of the Estuaries reports, we're taking an average of estimates from the Cachico River USGS gauge. In the Oyster, Salmon Falls, we were using the Lamprey gauge, and the Great Works, we were using the Cachico USGS gauging station. So combined, these tributaries represent about 40% of the combined tributary watershed area, and the Salmon Falls being the largest of those 3, it accounts for about 27% of the overall tributary watershed area. So now let's talk about area normalizing discharge, or what hydrologists refer to as runoff. I'll use that term here. The USGS typically reports discharge in cubic feet per second. So we're going to divide that by the area of the watershed. And then that will leave us, and if we use speed squared, we end up with units of feet per second, or we can convert that if we're looking at a daily average discharge to millimeters per day. You might also hear area normalized discharge referred to as cubic feet per second per mile, but my brain can't really follow that math. I can think about 10 millimeters of runoff leaving a watershed, and that's not just storm runoff. This is all the water coming off the watershed, from overland flow, from subsurface flow, from groundwater contribution, and from storm water. But it's everything reaching a certain point. So now let's look at all the data we gathered for this analysis. We grabbed all the data available for every USGS station in the Great Bay watershed that collected continuous daily discharge. And they're broken out here into different panels from different tributaries, and the different colors represent different USGS gauging stations. You can see a nice long record in the Lamprey River and a nice long record in the Oyster River. So now we're going to take these daily flows, we're going to sum them up for the entire year, in years we actually have the complete record, and then we're going to make some comparisons among the sites. So first, basic approach is to compare both USGS sites within a watershed and then between watersheds. So this example here, all axes are showing the annual runoff, so the millimeters per year of water leaving a watershed. The axes labels here, the LMP stands for the Lamprey River. I'm just using a simple 3-letter watershed code, followed by the area upstream of that USGS gauging station. So we're comparing here on the left, we're comparing the runoff at the upstream gauge in Raymond compared to the downstream gauge at Packers Falls near Newmarket. And here we have the red dashed line is the 1-to-1 line. And those points fall very close to the 1-to-1 line, just based on visual inspection. I do have some statistical analyses there, but it shows us that the runoff in this watershed is very consistent. Now we look over here on the right. I just chose to compare the Oyster to the Lamprey. They're neighboring watersheds, and they have the 2 longest records. So if we look at the Oyster compared to the Lamprey, again, lots of the points, most of the points are falling right along that 1-to-1 line. Maybe runoff is slightly higher in the Oyster than it is the Lamprey, but overall, on an annual basis, runoff is pretty consistent among these 2 watersheds. So now here, I don't expect you to read each of these individual panels, but this is a comparison of all of the USGS sites versus the 5 most downstream USGS sites that are still active. Here, this column is showing comparisons to the Oyster, the Winnipeg, the Exeter, Chico, and then these comparisons against the Lamprey. Here's the 2 examples we just looked at. And overall, just standing back, it shows to us that, look, their annual runoff is fairly consistent among all of these different comparisons. Now, let's take a look at the Salmon Falls River using historical data. And this is for the most recent gauge on the Salmon Falls that ended in the early 2000s. And this is the site a little bit downstream that ended, I forget when it ended, but it's a much older record. And when I look at the comparisons among all the different available USGS sites, I see that the Cachiko River actually has a very tight correlation for annual runoff with the Salmon Falls River. We have 9 years of data. I'm sure it might be great to have more, but we do span a nice full range of runoff. We have years where there's very low flow, years where there's very high flow, and all of those points are really following nicely along that one line. So this suggests to me that the Cachiko can be a very good predictor of the Salmon Falls moving forward. So now let's take those data and just talk about so how far off are we talking? Let's just put some percentages on it. So I'm showing here a box plot of all the different USGS sites compared to the Lamprey River, this USGS gauging station. It's the downstream gauge at Packers Falls, and the bars are showing you the kind of range in the percent difference, and the horizontal bars are showing you the median. So if we look here at our original example for the Lamprey, we're about, the upstream gauge in Raymond is about 3% higher than the downstream gauge. In any given year, you might be, 12% higher or 12% lower. So that's kind of your range in error associated with estimating discharge. For the oyster to the lamprey comparison, on average, you're about 6% higher in the oyster, and maybe that on an individual year ranges from 25 to -10. The number of years are shown across here. So again, I'm showing you these box plots for all the comparisons. We don't need to dive into those. What I wanted to highlight is that within watersheds, depending on what watershed you're looking at, the mean or the average percent difference ranges from -2 to 4.1%. That to me is pretty tight. On any given year, you're plus or minus 12, 13%. Again, that feels pretty reasonable to me, but other data users may want more constrained estimates. Now, if we go across all watersheds, we take the headwaters of the Exeter and we try to predict the downstream of the Salmon Falls. Our range is plus or minus 19% on average. And then any given year, you might be 40% lower, 50% higher. So again, that's if you're taking kind of odd comparisons, headwaters of the Exeter to the mouth of the Lamprey or downstream of Salmon Falls, probably not a likely candidate. Now, Jamie is focusing in again on the Salmon Falls because that's where we don't currently have a gauge, and across all watersheds are somewhere between -10 to -2%. Less runoff in other, if we base it on other watersheds, plus or minus 30 to 40% any given year. But if we focus in on the Cachiko, then we're talking maybe we might be off by 3% on average, and maybe that is plus or minus 10%, depending on what particular year we're talking about. So we're going to go back to that table that I showed before, showing the methods that we've been using previously. I also brought in what the DES uses in their assessment process and kind of what our recommendation is based on this analysis. So these green areas, we're not recommending any change. These upstream gauges are good predictors of downstream sites. For the Bellamy, I would say instead of averaging the Cachiko or the oyster, let's try to keep it a little bit simpler. Just use the oyster. That's the approach that DES would use, and I think that's a sound approach. For the Salmon Falls, I think we switched from using the lamprey to relying on the Cachiko, or data users wanted more accurate, more specific, estimates for daily or monthly flows, then work with the USGS to reinstate one of those historic gauges. And then, if the great works, again, I think that's the best approach available today would be to use the Cachiko River. And that's it. So we'll take questions. We get our slides at least.
Rich, can
Absolutely, Colin.
I'm trying to ask myself a question as if I hadn't thought about this quite as much as I have, because I'd like you.
Favor and just stop sharing so that everyone can see. Thank you.
So Bill and Michelle, tell me if I'm saying this incorrectly. The point of the discussion that you, especially your presentation, Bill, was about, hey, here's what we understand about how things are happening over time at sort of base conditions. And now, because there's questions in there, we wanted to do this extra research around what's going on if you sample during a storm. So it's important for everybody to understand that everything you said about in your conclusions, tell me if I'm wrong, are about what's happening as a result of storms, but not necessarily the entire picture about what's happening the rest of the time. And I'll tell you where I'm going with this. I'm trying to put together those are very interesting conclusions with what I read from the 2026 Mikulas paper, which had these correlations about, loading and storage, which were different than what we're seeing that happens during a storm. So I'm trying to, and maybe this is the right place to do this because not everybody has studied those two papers. We could do this at a later event, but I'm just trying to reconcile those two things in my brain.
Okay, so I think the answer is our question was about Great Bay's really dirty. It looks like hell, it's all brown and floating stuff all year. Where is that stuff coming? It's not being delivered dominantly by the river. So at the month, and that was, to my mind, a really open question because there's so much literature saying river flow, people. If you're going to measure sediment, you've got to look at how it flows. We've done that. These rivers are very unresponsive to flow. So, yes, I agree with your assessment. If we put that then in the context of the monthly data set that Mikulas paper was based on, we say, well, the head of tide estimate of sediment, which is pretty low, based on TSS samples, grab samples, take them to the lab and analyze them. It's like, yeah, those are actually fine to do monthly. I didn't think I would say that, honestly, because of my experience in other watersheds where it's like, oh, it's just like, no, you miss 80, 90, 95% of the sediment. Not the case here. And so the monthly samples were the basis of the Mikulas assessment. And they actually showed very similar results to what we see in the sort of instantaneous version in a storm, that the rivers are coming in at lower particulate load than, or particulate nitrogen, let's think, because that's one I can really picture in my head. The particulate nitrogen coming in the rivers is lower than the particulate nitrogen that's going out in the monthly assessment. So her assessment of the bay fits very well with, oh yeah, the bay is generating particles, and those are leaving in the we sampled at the end time. But so I think it's really very consistent, and it leads me to this project gives me even greater assurance. It's like, oh yeah, the bay currently during the and now we can say, well, during the whole time of the monthly sampling, it seems that was adequate for a suspended particulate material. For those 12, 15 years, it's been a generator of particles. It takes inorganic nitrogen, and it takes relatively clean river water, and it spits out more particles and more particulate nitrogen than what's coming in. Which of course begs the question, it's like, well, it's coming in, it's not coming in. There's more going out than it's coming in. Where does it come from? Well, it can be from internal generation processes. Nitrogen can be fixed and then turned into particulate, by microbes and turned into particulate nitrogen. Or the bay can be geomorphologically, it can be changing because we know sea levels are rising. And we know that big storms and big wind events can erode the bay shoreline. Maybe that's a dominant source of the particulate matter that we see. But one way or the other, this project solidifies, to my mind, the conclusions in Mikulas that the bay is sucking up inorganic nitrogen and so it's reducing the inorganic nitrogen load. It's removing it from solution, the dissolved nitrate ammonia. not so much DON. And it's generating particles, including particulate matter.
Thank you.
Can I open it to Stacy Villanueva?
Great.
Yeah, it's actually Clifton with
Clifton, sorry.
Stacy's link. But
Yep.
yeah. Thanks for this presentation, Bill and Michelle. We had reviewed your initial report and thank you for addressing those comments, sending out the other version today. And we just think this was really worth doing, and the kind of insights that we were hoping to get when MAM elected to fund this. I think I have a question related to colors, and I'm still trying to understand. It gets to the difference between baseline versus storm conditions. And this was related to one of my original comments, but in your report, you state that turbidity was generally highest during rising flood tides in the bay.
Yeah.
Now, was that outside of storm conditions? That was the highest, but it's actually highest during a storm? Or are you saying that the day-to-day flood tides is actually truly when it turbidity peaks?
The honest answer is I'm not quite sure, because in other words, both they may be comparable. The statement that was made about the highest sediment on the rising flood tide, it's like, yeah, that's based on our assessment of the Great Bay buoy data during these storm events that we sampled. But that doesn't mean it's different from what we would have gotten in baseline conditions. So I would have to go check that. Jody and I would check that and would like to include that then as some kind of a short amendment, addition, whatever, clarification of the report. It's a good question. And it does, so let me frame, I better understand, I think, where Kala and you, Clifton, are coming from. And it's like, oh, sure. I just showed you that the bay is really changing its turbidity load a lot. And so the McCoolus estimate of, hey, this is a particle generating place. It's not settling out particles, it's making particles. Well, maybe even making more than that budgetary estimate. My guess is it's probably making even more than that estimate suggested, but we don't know that yet. We have to look at the data. Because the storms, chances are, if you sample once a month, you're not going to catch a big storm. We had a hell of a time getting storms we could actually sample, and keeping the equipment going and waiting, whatever. Of course, it always happens. It's inconvenient for you. Yep. And so it could be that the particulate transformation, the fact that, we put out a lot more particulate than comes in based on the McCoolus monthly assessment, that may be an underestimate. But I'm not sure. We'd have to look at the one would have to, we can look specifically at what we were trying to say and verify it in our report. But there's a whole new level of assessment then that could be done. It's like, well, we've got these Great Bay records for turbidity. And we know it measures TSS, and it's, it's a good proxy for what's going on in the lake environment. It's like we have years of data, and we have plenty of data on river flow coming in. And we even have 12 years of data on the TSS in the Lamprey River flow, just as a backdrop. So we could address this question of whether the extreme events would alter our understanding of the whole processing of materials coming into this bay ecosystem and what gets out in the end. My sense is, I don't know. I don't have a good sense of it. We really need to dive into the data for all the records of the sensors, which data have been collected and have not been, we haven't tried to compare river and bay since the Maculas et al., not Maculas, Mullakula et al. Paper that looked at the Lamprey River gauge and the bay. And now we know that the Lamprey River gauge is representative of what's at the head of tide and more or less representative of all the rivers. So we could start to really constrain what's happening at a much finer time scale than monthly for the particles, which are so important for light attenuation. So it's a long answer to a question, but I think it's a centrally important question. Yeah.
Thank you, Bill. I have to drop off to my 3 o'clock, but I'll follow up with you on that.
Okay,
Great,
sounds
thanks,
good.
Clifton.
Okay, yep, bye.
Atsushi?
Yeah, thank you very much for your nice presentation, Bill and Michelle. I have read the paper published by Anna Mikris, 2026. All makes sense, actually. I have a question about CN ratio. So you show that the much higher CN ratio in the bay, about 12, compared to what in the river, which is about 6. I was thinking what's going on. Can the recent increase in phytoplankton or macroalgae biomass contribute to this increase in carbon to nitrogen ratio, or do you have any other explanation for that?
Well, yes, for sure. Your thoughts are sensible and sound. That yes, there's some material which is the source of the particles, which has a different seed-end ratio. To me, in fact, what's more striking than, well, what's in the bay, which is 12, it's like, yeah, that's okay, I'm not too surprised by that. I'm really surprised by my river estimates that I'm used to 25 in river sediments, in various places around the world. I haven't done that many places where we've done particular CNN. But for context, a maple leaf on the tree is probably 40 to 70 CN. The soil that's generated beneath the maple tree out in front of us here is almost certainly 25. A heavily plowed and worked agricultural field is probably 10. And this river at seed end of 6 it's like microbial. and maybe some algal plant material, or I won't hazard a guess. And yeah.
Yep.
No, go ahead.
Yeah, just a little comment. So I was asking the CN ratio in the context of recent significant decline in the eelgrass. So I try to think about what's going on. Maybe phytoplankton or macroalgae has prevented light environments in the bay. That's why we lost this eelgrass coverage. So this kind of context. So
Yeah. That's an interesting point. That's a really good point, because the zoster of the seed end is more like my maple leaf, I think. It's more like 20, 30, 40. And the algal is much lower. So it could be changing.
I just say one quick thing.
Absolutely.
Yeah.
Just super quick. We'll have to verify this with data. Everybody, this is Kalamazoo, but the data that I've reviewed and asked and talking to Chris and Trevor, over the last 3 or 4 years, there's not been much seaweed out there.
Yeah.
And maybe historically, we did see lots of more seaweed between 2000, a big increase between 2000 and 2017, 18. Maybe that got incorporated into the sediment or something, but I'm just saying over the last 3 or 4 years, I can't say with any confidence that the seaweed made the eelgrass go away. There wasn't a lot of seaweed out there. The light is so bad out in the bay that there's not seaweed anymore.
Yeah.
And seaweed doesn't even need that much light. So I just wanted to say that point. Sushi, I'd love to talk with you more about it offline. Go ahead, Gretchen, you wanted to jump in.
Well, I was gonna say, and I think this is one of the benefits of this venue or this setup is that you've got the scientists, and I love all the questions, and then you've got the practitioners, and so I'll speak kind of like I'm just a practitioner and I don't know exactly what to say.
This is, look, you've got to save our bay.
Right, so when I hear you say this, and I'm not a scientist, am I hearing there's relatively lower nitrogen coming from the rivers during these storm events, and is that what you're saying?
No, not exactly.
So what is it that you're saying?
So the storm events bring a lot of water.
Yes.
And the nitrogen content in that water is pretty much unchanged.
Yeah.
I mean, it's not radically higher, it's not radically lower than just a regular day.
Right.
Well, but actually all of it. I'm talking about particulate and all of it. Because the nitrate and the ammonium and the DON, they don't change that much. I see the Maculas said that the higher sea dump, but that was in the bank.
Yeah.
So my point is, no, rivers are really dominating the input. I mean, it's not that the river load of nitrogen entering the bay is pretty much just measure the water. In other words, just keep track of the liters of second coming in, and then apply a single correction for like, oh, it's 120 micrograms per liter nitrate in. Okay, then it's 120 times, 50 cubic meters. It's like that much nitrogen came in. So it's not that you have to sample nitrogen or all these different, during crazy storms. It's like, no, it doesn't seem like that really is necessary. But keep track of the water is, yeah.
So I was gonna say, so back to this very much the practitioner in the world that I they live in, really, with BMPs and stuff, or with the stormwater, we design the stormwater to really focus on just that first little bit, the first flush or the lower storms, and that's where you're getting your treatment, and then the larger ones are just kind of capacity. And it sounds like that sort of makes sense that as it's getting these larger ones, it's flowing out, but it maybe isn't. It's okay that that's happening because
so we've thought about this. Michelle and I have talked about it some. It's like, wow.
And you can think of
it's like, so my recommendation would be, think of it this way with the BMPs, is that the purpose of the BMPs is to try to slow down the delivery of water off this landscape. And that'll probably decrease the sediment, the particulate nitrogen, and it probably will decrease nitrogen a little bit, the dissolved nitrogen as well. But a major problem in the bay is these big storms are pounding through, and we don't know yet how much is okay. It's the tides, it's the wind, it's the rivers jetting into the bay. It's stirring things up and making it really hard for the eelgrass to grow. So if we can try to keep, as much as possible, there's also the temperature. I forgot. Holding the water back is going to ameliorate any temperature off hot asphalt. So we want to try to hold water back in the landscape as much as we can. And we don't have to worry about, making sure that this parking lot has this effect on TSS. It's like, focus on the water. Put your effort that way would be my professional opinion as a scientist but not a manager, but I don't think it changes much how you do your BMPs. It changes how you assess their effectiveness. And I would focus on how much do they dampen that, whatever the TR55 is called, the peak flow.
your peaks, which is interesting. That is, and I don't want to get into back and forth, but that is kind of an older way of thinking of just this detention retention versus what we kind of do now, which is a little bit different. But so it's good thing.
To me, it's sort of a good news, bad news story. The good news is that, these data do not suggest that you ought to be gone crazy wild with particulate control, worrying about TSS. Sure, follow BMPs, absolutely. But silt fences, but that shouldn't be like you do that, sure, absolutely. But the focus should be how can we engineer this landscape? I mean, maybe we need some wetlands along the edge of rivers. Maybe we need to bring back some of those soft edges that used to be, that are now pipes gone in off the street, right into the river. Those are the kinds that's where I would put my effort, thinking along those lines. Because when you do that, if you keep the water around longer in the landscape and allow it to interact with the soil, you get lower nitrogen, you get lower sediment, you get lower peak temperature, in the sun. Those are all bonuses, and you don't have to do too much except just to hold the water back.
We've got a hand up from Ken.
Hi. I was thinking about the BMPs and what you were saying, Bill, about them slowing the water pulse into the system. And we see that certainly in the salinity measurements out in the Great Bay, how quick they can drop with stormwater flow input. But I was also thinking from a hydrodynamic point, it's also going to, if you're slowing that water down, you're changing the tidal prism exchange of water and the shear stress on the whole system, which in of itself may reduce your resuspension of sediment in that system.
Yeah, excellent points. And so it really gets to, this is quickly, I'm a guy who understands watersheds, and I spent my whole career understanding how small streams, rivers, lakes interact with their landscapes and how it affects water quality, water delivery, and all that. We start talking about, okay, now the river goes into the bay, and it's like, I've got a lot to learn. So it's been really fun. But it's the interaction now is like, well, this pulse of water is ramming into the bay off these big storms. It's like, oh, and then if it's a really windy day out of the northwest, or there's a king tide, how does that affect what happens inside the bay? Because as Ken said, we know that water coming in, that radically changes the bay. Salinity can be down by 50, 60%, 70%. So, and it takes a long time for that to sort of work its way through. So I think understanding the hydrodynamics of what's going on, even more than we do now. I mean, we have, or are trying to get as much as we can out of the existing model that Tom Lippman built as part of our Eelgrass resilience. That's a key next step, I think.
Please.
So you, if I understood the story correctly, the DOM portion is a little different.
Yeah.
And while I'm speaking, I just want to, in a momentary lapse, you said TSS. It's either total suspended solids, or you could call it total suspended. But I actually feel like it might be important amongst this group to point out that it's not just sediment. It's a filter that captures a certain size, and if it's just size. It's not sediment. If you have a big enough phytoplankton on there, it's going to be recorded as TSS.
Yeah.
So I just want to make sure that everybody understands that. So the character of TSS can change radically depending on what estuary you're looking at.
100%. And I agree 100%. And it's important when I say, oh, TSS, suspended stuff, it's because the literature uses both, and they mean exactly the same thing. And what they mean is everything that's on a filter.
Right. So
that's all it means.
And Asushi has been sharing some data with me recently, looking at how, in terms of Asushi, for those of you who don't know, has been doing a lot of work on underwater light. What's going on in the water column to explain underwater light. Some of his recent work showed that in the bay, most of the TSS seems to be detritus, so it's organic detritus. Whereas as you go down out to the river and down towards Portsmouth Harbor, it starts to become mineral, mostly sediment, right? So what I'm trying to do is put together a number of stories here. You're saying DOM is driven by storms and is delivered by rivers. You also mentioned that DIN is coming in, according to McCoolus, and being converted to particulate matter.
Well, we don't know that it's being converted. We know that there's a loss of the inorganic, the nitrate, and the production of the particulate. It
Could be converted, but it
doesn't
could be
give us a
something else.
molecular,
Right.
you know, step,
Right.
but it's a plausible. Your scenario is 100% plausible. It's probably how it's probably important in our system.
So what I'm trying to say is that if all of that is happening together, and it's altering the sediment quality so that it's more, you just mentioned, oh, you got a big tide, you're gonna get more resuspension. Well, you're getting that resuspension because the sediment has now become very organic and light and fluffy.
Yep.
Right? That's why Portsmouth Harbor, I dive out there, it can be a really rainy, bad day. I still can see you underwater from 15 feet away. Because out there, it's cobbly, heavy sediment. In the bay, it's this fluffy, the organic matter is anywhere between 4.8% and 6%. And so I guess I'm asking you to come back and say, and out at Portsmouth Harbor, it's less than 1% organic matter. So I'm trying to connect. You're saying DOM is coming in.
Right.
Do we know, is that all leaf? Is it other kinds of organic matter besides just breaking down leaves? What is in the DOM that you're saying is coming in through the rivers?
Oh, it's mostly driven all by the trees and the wetlands.
Okay.
And so
the
it's a
DOM.
plant material. Now, that isn't to say that we don't have optical brighteners sometimes show up in the CDOM. And, you know, of course, there are anthropogenic sources as well. But my assessment is that it's almost entirely, and we see this as we look at predictors across the Lamprey River. We published this one across the Lamprey River subbasins that, you know, high wetlands, high DON, high CDOM, high anything you measure.
Okay.
And so the big difference with the rivers are clearly driving the input load and driving the concentration of yellow organic matter, CDOM, in the bay.
Right.
The particles, no, not so much. It's like, wow, there's very little particle load coming in.
Okay.
And that seems to be driven more by everything that's going on inside the bay. But the CDOM, I mean, the Mulakula paper showed that it's just a, you know, it's like, okay, it comes over the mouth of the lamprey, and then a day or two later, it's down in Great Bay, and then it slowly dissipates.
Okay. It's conservative, I think is what you
Right.
where nitrogen gets processed.
Now, that's for the color fraction. We don't know that the organic nitrogen, which is a small part of that color fraction, but important part, the organic nitrogen might be preferentially attacked by microbes and made available. So we don't want to just say it's inert, but it's as a bulk property of DOC, carbon that fluoresces, it's pretty much inert moving through.
Okay.
And having some light implications, but we know from our colleagues in the north, it's like, oh, we have waters that are as dark as tea. And eelgrass is doing great. So it definitely affects light attenuation, but it may not be a major factor than eelgrass.
Thank you.
I mean, this is so fascinating, and I feel like I can just ask so many really basic questions, but you know, again, we're the ones that kind of have to go back and think about, okay, now what? So I'm hearing a lot about these peak volumes, these peak rates, and I think that's something that's really important. But that is non-point source, a little bit point source, but not really. I mean, we're not getting big flashes.
No, we're talking rivers. Absolutely. The point source of nitrogen is very important because it's delivered right into the bay. It's in the form that the microbes and the algae and everybody can use. But the amount of water coming in, that's driven by rainfall runoff and the rivers. And of course, what's on the landscape? A lot of concrete. Well, okay, then it's like the river's moving responds differently, which we know from decades and decades of urban hydrology.
So is it the point source and these nutrient loads that it's creating what you use, the fluffy things that are in there, and then it's the large runoffs that's resuspending them? Is that kind of like?
It's a plausible scenario. Okay. I can't. So the question of what's the ultimate source of this? Oh, we can go into some serious limnology. There's it's called yitcha. It's this brown flocky stuff that was named 100 years ago by, I think, Swedish. I think it's Svante Odin, Swedish limnologist. We were just talking about Sweden this morning. It's like we don't know what it is. The dissolve we have a handle on, but the fluffy particulates, some can be formed by actually physically coalescing the dissolved material into colloids. Some can be formed by decomposition of everything. Mm-hmm. Leaves and dead fish and all of that, and it's all mixed together. Some could be formed by too much nitrogen accelerating the degradation of the peat carbon sort of backbone that's on there. We've seen that for Spartina down in Massachusetts, an experiment for 20-some years of what's all said pour nitrogen onto a Spartina marsh, and it's like it all turns to mush. It physically degrades. It's gone. So these, I guess the message there is, it's like there are dominant physical drivers, and there are these just sort of irrepressible biological connections across all these different, the carbon, the nitrogen, the fish, the Spartina, it's all interacting with each other. Mm-hmm. And the challenge then is, okay, if we're going to try to keep eelgrass in a functioning ecosystem in Great Bay, what are the levers that are most efficient to tweak to try to help the bay recover? And so that's why I find it fascinating, personally, because it's like, it's a complex problem that's just right in our faces.
Yeah. Yeah, it's obviously interesting for us too. And the levers you're talking about, we're talking about trying to pull levers too, balancing budgets and figuring out how to do things. So, yeah. All right, any other questions, remote questions? I think you're off the hook, but this is really excellent. Thank you so much.
Thanks again. Welcome. It's our pleasure. And again, thanks to Ma'am for funding this.
Yep.
I had wanted to do this project 7 years maybe ago. I proposed it at a Lamprey River watershed meeting. Okay, because this is pre-MAM, I think. And it's like, and everybody's just looking. It's like, okay, I guess nobody cares. But now we got to do it. It's really interesting.
I'd love to hear sometime about some of because you talked about it being dangerous to do this stuff during storms, which is absolutely true. And some of our MS4 permits do require, wet weather sampling during storms, getting out there and sampling, and you're sending your interns or whatever out in the middle of this storm down the side of the road to go hang out. I
safety is definitely
really don't care for that.
Yeah, it's not to be taken lightly. Especially, I'll say we're sort of through it now, but the shoulder season's like when the ice first starts to form, and then it's like, oh yeah, that looks pretty solid, and then it's not.
Yeah, that's terrifying.
And then the reverse, when we have these really cold rivers, and it's still ice and slippery stuff around, and you're trying to sample, it's like it's not good. You need to be
Okay, moving on. We've got stakeholder comment, and I actually don't see Melissa Paley or anyone from CLF here. So I'm going to move past that to other business. And one thing I want to say, and I don't want to get too much into this, but I want to acknowledge that the tier 1 is a tier 1 eelgrass report was recently unveiled to the prep management committee. Lots of folks have seen it. It was pretty dire. And so I just want to make sure everyone here knows that that's out there. I don't have really anything to report on that. Clifton and Stacy, who are MAM's sort of scientific assistants, have looked at that, and we're going to have to regroup. But it's really unfortunate and surprising how much eelgrass declined in 2025. And Cullen, feel free to, if you want to say something to that.
Yeah, I'd just say that we're going to think a lot about this morning. In fact, we had a meeting. Clifton and Stacy were there. We also had folks from EPA, DES, as well as Bill and Michelle, and our 3 external advisors. And I was saying earlier, I went into that meeting in a worse mood than I came out, because people who've been looking at estuaries all over the place say, this happens. And seagrass is resilient. If you keep doing what you guys are trying to do, reducing pollution, reducing non-point source pollution, slowing the water down, as Bill said, through stormwater, the seagrass will come back. And so you have to take the long view. So it was really nice to be assured of that by people who have looked at systems from Florida up to Prince Edward Island. And so we just it was really nice to see the consensus there. Everybody was like, no, this doesn't mean you're on the wrong path. This happens. You've had 3 or 4 really rainy springs in a row. That's going to have an impact on light. Now we're going to start putting seeds out there. We're doing more and more to put seeds in the bay, because the bay is a seed-driven system, whereas Portsmouth Harbor is mostly just existing roots. It's like one big clonal plant. So we're going to put seeds out in the bay. Well, what do seeds need when they're 1 centimeter poking their head out of the sediment on an April 20th? They need good light. So that's why all the work we're doing just continues to need to happen, and the seagrass can come back. If anybody out there who's in Zoom land wants to talk more about this report that the MAM kindly paid for and prep then wrote, please give me a call, and I'm happy to talk to you, come to your community and talk, because it's very complicated, but I want to assure that this doesn't mean seagrass is gone.
Thank you. All right, Colin. Any other business? Okay, scheduling next meeting. I had written July in the agenda, but I would like to do, and I think I spoke to some others, and Stacy and Clifton, we'd really like to do kind of early September meeting. Hopefully they'll have all the data that they're looking for, and they'll have pulled in some ideas for that report that we're looking for them to pull together. So I guess I know it's a ways out, but I'm thinking either a Tuesday or a Thursday in early September. I don't think we can. I don't know if we can do that right now on everyone's schedule, but I'll send out a like a doodle poll or something to the members to make sure that it'll work for everyone. And with that, motion to adjourn. All right, Dennis.
Second.
All right, Suzanne, all those in favor. Good to go. Thanks, everyone.
Thank you. Thanks, Bill.
Thank you.
Our pleasure.
Thank you, everyone.